All right, recorded is rolling. So it is Wednesday, November 16th, and today's going to be another work on the puzzles day. So you guys remember yesterday, uh, you had the class to work in teams and ask me questions on these. I did help you guys out with the first two, but I said I think you guys can get the rest of these. So now that you guys have had a chance to try these out, look at these, think about them, I'll go show you guys how to solve the rest of these. You guys big picture point of view, point out some things, make sure that since there's no multiple choice answers, just to make sure that you got these right. And then we should have about 20 minutes at the end of class that you guys can go check your work, do anything you need to do to study for tomorrow. So tomorrow, you guys remember tomorrow is going to be an in-class quiz. It will be open notes. So any notes you took last week, yesterday, today, it's software game. You can use those notes. You can use this page. You can use your homework. Speaking of this page, and I'll pick this up for you guys just sometime before spring break. Actually, it's probably a good idea to just go ahead and turn this in along with the quiz tomorrow, right? So use this for your quiz and we'll just start it in. All right, so what's we got? Oh, here, yeah, let's jump into this. All right, so like I said, yesterday we covered the first two. So let's move on to number 70, rockets. It says small rockets are used to make tiny adjustments in the speeds of satellites. One rocket has a thrust of 35 newtons. When you see that unit, newtons, guys, that refers to what kind of vector? Like a force, right? Newtons is a force, measures a force. If it's fired to change the velocity of the spacecraft, they gave you the mass in kilograms, okay, by 63 centimeters per second. Ooh, careful there. Right? Then what? How long should it be fired? Right? How much time? Right? So there's a big principle of how to solve this, and then there's a little detail you got to be careful about. So this is number 70 rockets. Right, like here's your rocket. They gave you the mass. You got to fire this thing. Okay. There's a force. Okay. Equal opposite forces, right? Right. So force. Okay. Number 70 rockets. Okay. And you guys remember impulse? You guys remember that if you apply a force for some time interval, I've been doing delta t for time interval, that's going to result in a mass times change in velocity of some object, right? That's an impulse change, right? If this were a graph, a force versus time graph would be the area under the curve, right? Or if this is an average force, or in this case, constant force for some time interval, okay? Yeah, you need a picture. Yeah. Right. So they told you the thrust force in newtons. So they gave you that number. Check. You just pop that in there. The question was, how long should the thrusters be fired? Which means you're solving for the time interval, right? Aren't you guys solving for the time interval? Right. They gave you the mass of the rocket in kilograms. Guys, kilograms. That's space. That's how units. You just pop that number right in there. Okay. And okay, now here's where you have to be careful. The change in velocity. Now, the target change in velocity, we want to speed this thing up by 63 centimeters per second. Can you just plug 63 in here? No. Right? You have to convert that to base SI units, which would be like meters per second, right? Guys, how do you go from centimeters per second to meters per second? Divide by 100, right? Right. Guys, how many cents on a dollar? 100, right? So you're plugging 0.63 meters per second in for here, right? And that will give you base SI units. And therefore, the time will naturally come out to be what unit? Seconds, right? Seconds, right? I think it's a crazy big number of seconds, but that's what it gives you, right? Now, if you wanted to go an extra step and say, like, oh, that would also be like so many minutes or something, you could do that. But if you just solve it with newtons, kilograms, and in meters per second, it'll naturally come out to seconds. Next one, number 77. A rubber bullet. They call it a 12-gram rubber bullet. Guys, grams. Is that a base SI unit? No. Right. What do you when you eventually plug in this mass? You can't plug in 12 for grams. You have to convert it to what first? Kilograms. Right? Especially since the other mass involved is given in kilograms, right? I mean, at least they have to be the same unit. Right. So let's just put everything in kilograms. Just be super safe. Right. So 12-gram rubber bullet, I would call it 0.012 kilograms, right? grams to kilograms, is that 3 decimal places, right? Divide by 1,000. Right. Velocity of 150 meters per second. So looks good. Hit the stationary concrete block. They gave you the mass of the block in kilograms. Oh, it is on a frictional surface. So that kind of reminds me of Magic School at baseball field. Sometimes I say air hockey table. There's no friction. Okay. Ricochets. Ooh, fancy word, ricochet. So is it gonna boing, bounce off the opposite direction? Okay. Yeah, maybe it's I mean it's pretty close to elastic, right? Maybe it's coefficient restitution of like 1 year or something. I don't know. We could find that too, but oh, and look how nice they were, you guys. They told you that the final velocity of the bullet was a negative number because they could have been really tricky. They could have said it ricochets off at the speed of, and then had you guys have to figure out that it would be a negative number. But the fact that boing changes direction, comes back in the opposite direction, that's a negative velocity, right? And so how fast will the concrete be moving? I think with this one, it sounds like just general conservation of momentum. So the framework for solving this is that the sum of momentum initial is equal to the sum of momentum final, right? Now this could be a closed system between the bullet and the block, right? Now the momentum initial is all provided by the bullet. It'd be the mass of the bullet times the initial velocity of the bullet, right? Now I could say plus the momentum of the block, but the block just starts at rest, so it'd be like plus 0, right? So all the momentum is supplied by the moving bullet, right? Small mass, large velocity, okay? And then it's gonna slam to the block where they bam, and then post collision you've got 2 objects that are both in motion, right? So I'm gonna say the same mass of the bullet that there was before, which again you had to convert it to kilograms first, okay? Times the post collision velocity, so v bullet bullet final, okay, plus mass of the block times v block, also final, but I'll just call it v block, right? You guys get that? All right, so the most question, how fast will the concrete block be moving? How fast will the concrete block be moving? Okay, that means you're solving for this. So hopefully we have everything else, right? Okay, now they told us they gave you the mass of the bullet. Now you do have to convert to kilograms. So grams to kilograms, divide by 1,000, and check goes right there. Just a couple lessons. Okay. They gave you the mass of the block in kilograms, so you just pop that right in there. Okay. They told you how fast the bullet was going. Did it say meters per second? They did say meters per second. All right, how nice of them. You can just straight plug it in. All right, no conversions necessary. Okay. And they also told you the rebound velocity of the bullet. They told you it was negative. Oh, I want to mention this detail too. Look, they gave you scientific notation. Negative 1.0 times 10 to the 2 meters per second. What's more colloquial way to say that? It's negative 100. Yeah, negative 100. Can you just take negative 100 and pop it right in there? Right? You guys see how you have one equation, one unknown? You guys can do a little bit of algebra to solve that. Right? Right. Any questions so far on either the first two? Right, you guys good? Right. So impulse question, conservation of momentum. Right. Next one, number 78, skateboarding. Oh yeah, there were a few students who asked me about this one yesterday. Skateboarding. We got Kofi with a mass of so many kilograms riding a skateboard with a mass of also so many kilograms. Hey, look at that. Mass of skateboard is a lot less than the mass of the person. I mean, that makes sense, right? Okay. It's both kilograms. How nice. Right. So no conversions necessary. All traveling at this initial velocity of so many meters per second. Yeah. Right. Kofi jumps off and the skateboard stops dead in its tracks. In what direction and with what velocity did he jump? Right? So 78. Okay. I'm thinking there's like the skateboard, very low mass. Here's Kofi, right? Much larger mass. Right? They're both moving together, right? So the same velocity because they're all together, like kind of like one giant object. Then Kofi's gonna bam jump off, and the skateboard's gonna come to a dead stop. So if this is Kofi and this is the skateboard, right? You guys follow it? Be like this, bam, and you guys see how the skateboard, bam, came to a dead stop? Okay. So I bet we can use just conservation of momentum to solve this too. In fact, if you filmed this and you ran the film in reverse, would it look like would that look like a perfectly inelastic collision? Right. So we saw a few like this. You guys remember one to throw in the baseball, Magic School Bus, or the grenade exploding? Sort of like an inelastic collision in reverse. The framework is still conservation of momentum for this like closed system we're going to treat this as. Okay. And it starts off with mass of Kofi plus mass of the skateboard times the initial velocity, right? Isn't it like one giant mass moving at the same velocity? Right? But then after he jumps, right, we got two different things going on. We got mass of Kofi times velocity of Kofi, right? Plus mass times velocity of the skateboard. But the skateboard, the fact that it comes to a dead stop, that we just plus 0. So you could write that as a term, but you just be multiplied by 0. So it'd just be plus 0, wouldn't it? Right. So really it's just that. Right. So they told you the mass, they told you both masses. Check, check. And also it shows up here, check. Okay. They told you the initial velocity, check. Oh, so you guys see, you're just gonna solve that. Okay. Now there's a, so you plug in the numbers. It's just one algebra step. You're just gonna divide by mass of Kofi, and then you get the answer. Okay. There's one last thing I want to mention about this, which is that this is actually a simpler interpretation of this problem. Okay. What I'm assuming is that we're measuring everything with respect to something that's not moving, like maybe like a nearby tree. Like if there's a nearby tree, maybe there's like a, like a guy with a radar gun here, and he's like, measuring all the speeds, like something that's not moving off the side. Okay. Okay. Now, a more complicated interpretation of this, when it says like how fast does Kofi jump, you could say Kofi relative to the skateboard, and the fact that the skateboard like rebounds, you say, okay, that'd be like an extra complicated step. But I mean, I think if you do this, that should be good enough. This is like a simpler interpretation. Okay, guys, good with that? All right. 79 I'm going to skip and come back to. I'll come back to that one. But let me just knock out these two down here. 86, ice hockey. A hockey puck, they told you the mass of a hockey puck. Oh, and they gave you kilograms. Right, how nice. 0.115 kilogram. Hockey puck moving at 35 meters per second. Yay. Strikes a jacket, and they gave you the mass of that jacket that was thrown onto the ice by a fan of a certain hockey team. I feel like that's some kind of illusion or something. I don't get it. I don't know if something historical happened. I don't know. The puck and jacket slide off together. Ooh, does that sound like perfectly inelastic? I think that's just straight up perfectly inelastic. 86. We got ourselves a hockey puck. I'll call it mass puck. It's moving at velocity puck. Right, there's this jacket. Right, I'll call it mass jacket. It just starts off at rest. Okay. So here's our framework again. Sum of momentum initial equals sum of momentum final. Right? And in this case, all the momentum is provided by the moving puck. Right? Just like a few questions ago, all the momentum was provided by the bullet. Right? And the block was just sitting there. Right? So it starts out kind of same idea. Right? We got mass of the puck times initial velocity of the puck. Right? And then when it collides with the jacket, the two slide off together. It would say mass of the puck plus mass of the jacket times the final velocity of the two, like slide off together. Okay. Oh, also, anytime you see anything on ice in a physics textbook, the assumption is like there's no friction. Right? Did they explicitly say that? I don't know. That's usually the running assumption in time moving things on ice. Right? So don't worry about friction. No frictional forces. This can just be a closed system. Okay. Right? So they told you each of the masses, the puck, the jacket, and the initial velocity of the puck in meters per second. Everything's in base SI units. Can you guys just solve for that? Right. So you take the combined mass, divide it over here, and then boom, you got your answer. Okay, guys good? All right, so we just got 2 more to go. All right, and then you guys have the rest of class to work with each other, help me out, or, ask me for help. Number 80, a 2575 kilogram van runs into the back of an 825 kilogram compact car that had been at rest. They move off together at 8.5 meters per second. Friction is negligible. Calculate the initial speed of the van. Okay. Okay, so that actually sounds very similar to what we just did, except that it's solving, instead of solving for the final condition, now we're solving for the initial condition. So what do we do? Okay. So we got sum of momentum initial equals sum of momentum final. Right? It's a collision, so that's going to be the framework. Right? In this case, the momentum is provided entirely by the moving van because the car had been at rest. So I'll say mass of the van times velocity of the van, which, by the way, is what we're eventually solving for. Okay. So say plus 0 for the car, so whatever. Okay. And then equals, and then they couple together. So mass of the van plus mass of the car times final velocity of the two stuck together. Right. That was basically that, right? Just straight up inelastic. Okay. They gave you the masses. They gave you the post-collision velocity. Yeah, this type of thinking might be handy one day if you are a forensic investigator, you see some car crash, look at the skid marks in the road, and this might be one of the steps that you solve along the way to figure out, like, who was traveling how fast to start with, and use that fault for blah, blah, right? Okay, kids, just take the original mass and draw it over here, and boom, you got your answer. Okay, guys good? All right, so tell you guys this. All the quiz questions we've covered so far, the quiz questions tomorrow, here's what they're going to be. Okay. They'll come off, they're going to be some combination of some of the circled questions that we've done so far, some of these problems, right, that we did between last week and this week. Right? And also, I asked you guys a couple of questions, or you guys can see this tomorrow. You guys remember like the putty going to the bowling ball and the bouncy ball boing bouncing off the bowling ball? Right. So that question's going to come up. That was a big starter question yesterday. It's all on Google Classroom. If you need to go review any of that, it's all up there. Or you can ask me later. But there's one more I want to cover. That it's not going to be on the quiz, but we're going to take this to another dimension. It involves these billiard balls. Right. This was going to take a little while to go through, but it's a little more complicated. But once you guys see the big picture of how this works. Okay. So now we've got like a two-dimensional type collision. Right. So only one of these you guys are going to see. We've got a cue ball with this mass moving at this velocity. Bam! Strikes this other ball. And then post-collision, they travel off at 45 degrees to this x-axis, 145 degrees above the axis, 145 degrees below the axis. Right? And that's all they give you. They gave you the mass of each ball, the initial velocity of the cue ball, and the directions post-collision. And the question is, what is the velocity of each of the balls after the collision? Now, before I set up and solve this, since I kind of know where this is going, one thing that I think is interesting about this is that the actual mass of the ball ends up not mattering. The fact that they're the same mass, they could have given you any mass, and the fact that they're the same masses, the answer would be the same. So when I go through and solve this, I'm just going to call mass m, and I'll show how it cancels out. Right. Another thing is that one of my students earlier asked, hey, would this be perfectly elastic? And we're going to run a check at the very end of the problem. So we're going to answer this question they actually asked. And then we'll go do a check to see, is it perfectly elastic? And I think it's kind of an interesting result. The fact that all they gave you was just a little bit of information. And one of these pieces of information ends up canceling out anyway, right? That you can answer a question like that. And so let's tackle this thing. And so the principle that you're using to solve this is that momentum is conserved in each direction. Let's say like along each axis. So here. All right. Forewarning you guys to do, I'm going to put this all on one piece of paper. If I went to like the nitty-gritty of every single step, it would probably take a few sheets of paper, but I'm going to simplify some things, use some symmetry, and I want you guys to see the big picture of this. So it's all going to be on one screen on one piece of paper. Okay. So here's my axis system. I got this x-axis. I got this y-axis. Okay. I got this one ball just hanging out here. It's like la-di-da, mind's own business. And here comes along another ball, and bam, like strikes it here, coming in from the left. Pop. Okay. And then each of the balls is going to move off a different direction. We got one ball heading 45 degrees above the x-axis. Right, so this could be either velocity or momentum vector, depending on your point of view. And then we're going to solve this through momentum because there was a collision. So maybe that's the way you want to think about this. Momentum vectors, right? This other ball goes down this way. Okay. So they told you this is 45 degrees, and this angle is 45 degrees. Right? Right, all right. Okay. Let me add a little bit before. Right, so let me go back before. Right, there was this ball that was coming in. Okay. I'm going to label the mass M. Okay. Now they did tell you the math. You can plug it if you want to, but I'll show that it cancels out. Okay. And it's coming in at 4 meters per second. I guess it's sort of like a velocity vector, but mass times that velocity would be like momentum, right? So M times 4 kilogram meter per second. Right? You guys got that? Right. So here's what we're doing. We're going to say that the sum of momentum in the x direction before the collision equals the sum of momentum in the x direction after the collision. So along this x-axis. So this 4 times m units of momentum is conserved along this x-axis. Right? And this is also true along the y-axis. So the sum of momentum in the y-axis initial, let's say before collision, equals the sum of momentum in the y direction post collision. Say F for final, like post collision, right? Right. So we can sort of set up like a system of equations with that. Right, you guys get that? Okay. All right, so here's our setup. Here's our framework for solving this. Sort of thing like a two equation system of equations type deal. Right. All right. Because there's a lot of ways we can go with this. How about this? Let's work on this geometry a little bit. You guys know 45 degrees. Guys, if this is 45 degrees here, what's this angle right here? Yeah, also 45 degrees. And what's this angle right here? Also 45 degrees. Right. So you guys know that, right? Okay. Maybe it's not 100% necessary, but it could help. Could help a little bit. How about this? If we're keeping everything along each axis, because again, momentum is a vector, that's why I'm doing the setup. Okay. I'm going to split each of these momentum vectors into vertical and horizontal. Right? So I'm going to split this into components. So the one going up to the right, well, it's kind of going up, kind of going to the right. I'll go up first and then to the right. I think it'll just fit on the paper a little bit better. Right? Although you could go right first and then up, that's fine too. Right? And the one going down to the right, it's kind of going down, kind of going to the right. Right? So I'm going to split that into components. Right? This is something that we've been doing since I think like first or second week of school, they split things into components, right? It keeps coming back over and over and over again in this class, right? Right. What's that? All right, all right. Right. Again, I'm giving each ball a mass of just plain m. It's going to cancel out at some point. Okay. And what we're solving for is what's the velocity. So if these are momentum vectors, I guess this would be like m times 4 meters per second. This would be m times v final in this direction, and this guy's going its mass times its velocity in this direction. Okay, something like that. Okay. Now, I've already sort of started to solve this inadvertently, but I'll show you what I mean. Right? You guys see this bottom equation? The momentum in the y direction is conserved. Right? Well, before the collision ever happened, when one ball was just sitting there, one ball was moving strictly along the x-axis. What was the momentum in the y direction? 0. Right, there was nothing moving up down. So after the collision, bam. Do you guys think that the upward portion and the downward portion have to exactly cancel each other out? One's positive, one's negative, right? That's what you can really get out of this. Again, I'm not writing that down because that would take several sheets of paper when I solve it properly. But what this says, like the big picture interpretation that I want you guys to see, what this means, this bottom setup, is that this part cancels out with this part. Has to, right? Now, if the masses were different, then this would start to get pretty complicated pretty fast, although we can still solve it. Okay? But the fact that there's the same mass means that if these components of these momentums are the same, and also the angles are the same, right? Then doesn't that mean that these momentum vectors are the same? And in fact, the masses are the same, the velocities are also the same. Okay? So I labeled this velocity via, and I labeled this velocity also via, but that's the thought process for why they are the same. Right? So they will have the same velocity. Right? You guys got that? Okay. Next deal. Let's do. Right. Let's do this top equation. Right. Sum of momentum initial equals sum of momentum final for in the x direction. Right. So I think I can put that over here. So I'm taking this top expression. I'm saying the initial momentum came all from this guy. Right. This mass times the 4 meters per second. Right. So I'll say some generic m for mass times 4 meters per second of velocity. Okay, that's supplying all the momentum to the system. That's before the collision. Equals, and then I got after the collision. Now, after the collision, isn't it these two components right here? Right? Okay. So, I meant to jot that down. So let's do this. Okay. Would this component here be the mv times sine of 45 degrees? Right. Or we can play out this angle, say cosine 45 degrees, but it's the same thing. You guys know sine of 45 degrees, cosine 45 degrees is the same thing, right? Okay. So let me prove that to you guys. Okay. Sine 45 degrees is 0.707. Cosine 45 degrees is also 0.707, which is called the square root of 2 over 2. Here, show that to you guys too. Square root of 2 divided by 2 is 0.707. You guys see that? Okay. So is it okay if I call this component right here the square root of 2 over 2 times mv naught? Or final, mv final. Is that okay? Okay. And that would also be true for this guy down here. Okay. Is square root 2 on 2 times MV final. Right? You guys get it? Okay. And if you take that component plus that component, it has to add up to the original momentum, right? Which I've started the equation right here. So this is going to be root 2 on 2 MV final plus another root 2 on 2 MV final. Right? You guys get that? That's set up. Okay. So here's your initial momentum, mass times velocity. Okay. And here's where we went to. This component plus this component, which is like this plus this. Okay. And again, I know they're the same velocity because of the y direction information, which I just walked through you guys verbally. Okay. You guys get that? Right. So now let's just do a little bit of algebra. All right. If you have something over 2 and the same thing over 2, can I just add those together and say that'd be what? Square root 2 MV final? Okay. Also, here. Okay. You guys need 1, 2, 3 terms? Do you guys need 1, 2, 3 algebraic terms? You guys get? And they all have what in them? The M. So it turned out it never mattered exactly what the mass of the ball was, as long as they have the same mass. Mass goes away. Okay. So now we went to the fact that we just scratched out the mass cancels out. So you could have plugged it in, that would have been fine too. Now I'm gonna have some velocity values. 4 meters per second is equal to, okay, root 2 over 2 VF plus root 2 over 2 VF. Isn't that just like plain root 2 times VF? Would that be true? Okay, guess that. Okay. And now we're one step away from answering the question that was asked in the book. What is VF? That was the question they asked, right? What is the velocity of each ball? Okay. Just divide both sides by square root of 2. So 4 divided by the square root of 2 is this number right here. V final is 2.8, I'll round up a little bit, 2.83 meters per second. Okay, so 2.828 or something. All right, so it's about that fast. Okay, guess that. Okay. Right, and I told you guys I wanted to do one more thing with this, which was look at kinetic energy before and after. Because, I forget if I said it that way, but that would help you verify if it's elastic or not, right? Isn't that a property of elastic collision? If it's perfectly elastic, like this right here, it's pretty close to perfectly elastic, then obviously momentum is conserved. That's just like a law of nature, but kinetic energy would also be conserved, right? So I want to know, here, maybe I'll break out the pinky right here. What is the initial kinetic energy and the final kinetic energy? So if they K naught, here, let's go ahead and throw in mass, right? But, I know I canceled it out, but on the paper they said it was 0.6, yeah, there, yeah, thank you, 0.16 kilograms. Right, let's do a kinetic energy check. So K naught, the initial kinetic energy is, you guys remember it's 1/2 mv squared. Right, so just put in the calculator here. So that's 1/2 times the mass of 0.16 kilograms times the initial velocity of 4 meters per second being squared. I'm looking at 1.28 joules. Right. So when just the cue ball was rolling towards the other ball that was at rest, there was 1.28 joules of kinetic energy. Right. Right. Now let's see post collision. How much kinetic energy is there? Okay. Now there's really only 2 possibilities. One is that there could be less kinetic energy after than before. In fact, realistically, that's what you would expect to see. Right? Or you could have the same kinetic energy. And if you have the same kinetic energy, then you know it's a what kind of collision? Perfectly elastic, right? Can you ever, post-collision, have more kinetic energy after compared to before? No, you can't. Not just for a regular collision. Maybe if a grenade explodes or something, right? Where you have an input of energy, but otherwise, no. Right? So let's figure it out. Let's do K final equals, right, now I have 2 individual balls that each have this mass moving at this speed. Right? You guys remember kinetic energy is a scalar value, right? So I don't care about 45 degrees or anything anymore, I just care about speed. Let me get an exact speed because it's 4 divided by the root 2. So going back to this crazy long decimal that represents that, right? So we do 1/2 times the mass of this ball, 0.16 kilograms, times that speed, I'll just say the answer squared, okay, plus the other ball also doing the same thing. 1/2 times its mass times that same speed squared. Right? So moment of truth. We're about to find out if this is perfectly elastic or not. if the number on my screen says 1.28, then we know it is perfectly elastic. Right, which might be true for a billiard ball. Let's find out. It is. It is. Look at that. 1.28 joules. So in fact, you do know that this is perfectly elastic. Right. Which looked in math, but it's a nice thing to check in. Right. You guys get it? All right. So you guys got the rest of the class to solve problems, ask me any questions, get ready for tomorrow, and yeah, answer any questions you guys have. What's tomorrow?